Testing.
One more time.
Can you hear me?
Got it.
Awesome.
All right. Good to go. All right. Ready when you guys are. We are live. Brilliant.
All right. Hey, everyone. My name is Bharath Sitaraman. I'm a product manager at Pivotal. I'll be talking to you guys today about GPText, which is our text analytics built on top of GPTB. So I've been with Pivotal for just about 5 years now in various capacities. Originally a developer on this project and then switched to a couple different teams before I decided to come back to my first love. So today we're going to be talking about GPText 2.0, which is Pivotal's in-database text analytics for big data. So before I get into that, I'll give a little background. So you guys are familiar with GPTB and SQL databases, and they do have this concept of indexes, but why can't we use a basic index for full text search? So let's take a look at this phrase. GPTB is an MPP database management system. So the first order that you would go into doing with an index is you tokenize it, split it into the array of words, in this case with the white space tokenizer. You move it all to lowercase, so you're normalizing the data. And then finally, you can stem it using Porter stemming or any other algorithm that you might want. And on top of that, you start building your binary index. Or in another case, you can use a gin index as well. So here's kind of a basic structure that you would have with the database index. So you have it broken down for this given record. So it has the words as well as the links to each of them. Now what happens if we query cool MPP database? We're not going to get an accurate representation of the results. But why is that? Well, first of all, there are a lot of different natural problems. First, each term for each document would be stored many times. So especially when you have a bunch of different unique words or even common words stored across multiple documents, let's say millions of records in your table, you're going to have each word. So let's say database appears across 1,000 of the documents across like 10,000 records. You're going to have 1,000 different words in that index, and it's going to be stored 1,000 different times. This is not cost effective in terms of space and storage. The other thing is, how do you estimate which word is more important and which one is not? You'd have to search through all the records individually in order to understand, okay, how many times does this appear across the multiple records, and how important is this word? Like, how much weight do I give to this word? How do you handle the complex queries that require exact phrase matching? So for example, if you're not searching for individual terms, but you're searching for actual phrases. So in this case, like cool database management system, like all is one phrase. Or how do you rank the query results? When you don't have that holistic view, or at least an easy way to see that holistic view of the database, of the index and the words that are in it, how do you do accurate query searching and query results? This is where Solr enters. So when Solr looks at a bunch of different records, it goes through 4 main tasks. One is pre-processing the data before putting it into an index. The second is having an index structure optimized for full text searches. The third and fourth are processing the incoming queries quickly and being able to rank the results based on how well the query itself matches each document. So let's take a look at the pre-processing steps. Well, in terms of pre-processing, it actually goes through a couple different steps. And Solr itself has multiple ways that you can process the text using something called analyzer chains. So in this case, this means looking at tokenizing the words, then removing stop words. So any common words that you might have, like a, at, the, from, etc. Being able to stem the words, and also being able to normalize the words. But other things that you can do are also protect the words. So let's say we want to protect Pivotal from being modified any further, or common words that are company names. You might want to prevent them from being modified within the index. You can do that. For international text, being able to search through bigrams and pair certain characters together, you're able to do that. So Solr really provides this enhanced flexibility and configurability when it comes to setting up your index for a given set of records. Then how is the index itself stored? So here's kind of a high-level overview. You can see that it stores it as an inverted B-tree index. So it's a prefix tree with positions. So rather than going back to this index where each document has a list of terms and you store this individual tree for each one, you have a massive tree of terms and you invert it. So in this case, we can see GPDB or GPText. For example, GPDB is stored in document 1 at positions 2, 10, and 25 within that document. Grass is stored in document 2 at these positions. So you build this inverted index, which is a lot more cost effective. Plus, you can see the links and you can see that it's stored across multiple documents. So you can see an individual term, what docs is it stored in, and where and how many times does it appear in each of these documents. Now, what can we do with this? When it comes time for the actual search, you can rank the results using token relevance. So Solr itself provides something called TF-IDF, which is the score and ranking and relevancy system that they use when it comes to searching across your set. So what it means is term frequency inverse document frequency. So let's split that up into 2 parts. The term frequency is talking about how many times does an individual term appear in a single document. So the more times that it appears in a document, the more important it's going to be, the more weight it's going to place on that particular term. Versus inverse document frequency, which means across the whole set, how many different documents does my term appear in? So if you say, for example, Greenplum appears in documents 1, 4, and 10 out of 10,000 documents, and in each of those documents it appears 1,000 times out of like 2,000 words, it's going to place a lot of emphasis on those documents because it appears so many times, and it's in only those documents out of the whole set. So it places a lot more weightage on it. So basically, you're multiplying the term frequency in a given document and the inverse document frequency. How sparse or how popular is that word? The more popular it is across all the documents, that means it might not be as individual or as unique of a word when it comes time to search for it. So where does GPText come into all of this? So we talked about kind of a background in terms of why Solr is important for text analytics and the enhancements that it's made on top of just in-database searching. GPText essentially combined the 2 worlds. So what we're doing is we took Apache Solr and placed it directly on top of Greenplum database. So you get the flexibility and the configurability that you would with Solr with different analyzer chains that you can use, the configurations that you can use, but you get the familiar SQL interface as well as the scalability that you would with Greenplum database. So we can process mass quantities of raw text data for large-scale text analytics. You can support the semi-structured and unstructured text. So you can search across an individual text body that's in one column and then filter by the other columns. So you can say, I want to search for these terms, but I want to filter by all documents that appear only in the last 2 months and were authored by X user. So you have that join between the structured and unstructured data. And an advancement that we have is you can leverage MADlib for statistical machine learning. So by looking at the documents, we enable them in such a way and expose them in such a way that you can use MADlib for clustering the documents or classifying the documents accordingly if you have new terms that are coming in. And everything is exposed as a SQL UDF, which means that it's the familiarity of your SQL interface, where it's just SQL functions rather than having to write curl requests or having to write complex MapReduce to query your data. When it comes to the architecture, GPText is highly available. So following the GPDB architecture, where you have your database table that's split across multiple segments, we follow the same structure. So when you have your index, each shard maps to the given segment, given database segment. And the high availability part comes in where each shard has a leader replica and certain follower replicas. Similar to where you have your Greenplum architecture with primary and mirror segments, you have a leader replica and follower replicas. So if any of your replicas go down, as long as you have one copy of each shard still up and running, you're fully operational. You can still index, you can still query your data, you can add new data into the table as well, and the index. And at the same time, you're providing this sort of distributed manner. So the way you have your SQL queries that are distributed across each of the segments in this MPP architecture, your Solr queries or your GPText queries would be distributed across these individual shards in parallel as well. So what are the advantages versus some of our leading search engines and search engine databases that we have? So in this case, Solr and Elasticsearch are number 1 and number 2. And how does GPText fare against that? So as you know, GPText is essentially taking Solr and putting it on top of GPDB. So we have a distributed version of Solr. So we provide that high availability, and we provide the MPP architecture. So you get much faster results by leveraging GPDB. We have support for multiple formats. So in the same vein, CSV, XML, and JSON with the Greenplum 5 release coming out later this year. It's easily configurable, so you can just use a simple management utility to manage how you want your indexes to be stored, which analyzer chains you want to use, what sort of configurability in terms of memory and resource usage you want. So you have a lot of leeway and ease of use in terms of how you want to configure your system. When it comes to analyzer chains, we also added some extra capabilities on top of Solr. So we added 2 new chains basically to process international text, whether it's Chinese, Japanese, Korean characters, Russian, Hebrew, whatever. You're able to handle it all in a single index if you have multiple languages. And more importantly, we also have social media analyzers. So being able to look through your Twitter streams, your Facebook streams, etc., and parse out hashtags or URLs or even mentions of particular users, you're able to search for that in your stream. The other thing is the unified query parser. So we provided an all-in-one interface to be able to use multiple different query parsers at once. So Solr provides this query parser, different query parsers, either to do complex queries for regular expressions or surround queries if you're looking for proximity searches, or even just basic Boolean searches using the Lucene query parser. However, if you wanted to combine them, you would have to write different queries and do these complicated joins between them if you wanted advanced search querying results and capabilities. What we did was we essentially abstracted that all into the backend. And so you can write a complex query where you're searching for term A and term B and a complex regular expression within 3 words of another expression that you might have. So you can get as complex as you want, but you can combine the different types of query parsers all at once. And most importantly, we also have advanced analytics with MADlib. So as I mentioned, we expose the terms and the dictionaries in such a way that MADlib can use it for clustering or classification. So what are the different use cases that we have here? A couple of ones that we've exposed through customers. For example, after the 2008 crash, many of the banks on Wall Street and many of the firms on Wall Street were looking to do more strict regulation and compliance. So they have multiple emails and chats and internal company documents, and they're also looking through government regulations to make sure that they're financially compliant. So we're able to index and search through all of those and correlate it with the internal company data and actions that people are taking in order to make sure that these Wall Street clients and firms are still financially compliant. Another thing is health records and medical diagnostics. So being able to look through patient EMRs and doctor's notes, as well as the structured data such as a patient's height, weight, any past symptoms, or cholesterol, any of their medical statistics, and look at that data and be able to look for either easy medical diagnostics or possibly risk of insurance, high risk of insurance or insurance fraud. Another one is part monitoring and recalls. So being able to read through mechanics notes or service centers notes for example, with the auto industry or with the electronics industry, reading through these notes and understanding what parts are failing easily, what parts are not, and being able to issue recalls much more quickly, or be able to understand what are the components that we need to fix in future releases. And of course, in terms of national security, being able to monitor data from various data sources in order to understand risk of threat against a company or a country. Sorry. So I'll give you guys a demo at this point. So here we have small Greenplum instance. Yeah. Is that better? I'll move to the side, so you guys can see. So just a small Greenplum instance that's running a small table of about 50,000 records. So this is a classic data set that we're using called the Enron data set. It's been public. It's basically a collection of about 50,000 emails that have been made public after the whole Enron story a couple decades back. So let's go here. So I'll show you how quickly it is and how easy it is to create an index and start searching. So here we have Yeah, 49,999 rows. And just to show you, these are emails that contain IDs, the folder, to, from, and also subject and content of this data. So let's create an index. So here we're specifying the schema and table name, the unique ID that this table has, and the default search field. So when we're actually indexing the data, which will be the next step, we're indexing all the data that's stored in the table, or you can specify any subset of all the data that's stored in that table. But when you have a default search field, anytime that you issue a search, it's going to be searching on that field. But you can specify other fields if you want to filter across from them. So we're enabling terms. So this allows us to see like the term vectors, the terms and their positions in the documents, which will be also useful for highlighting search results when we want to highlight them. Let's say we're building an application on top of this. Let me just pull this up. So we're going to index this data. In the meanwhile, do we have any questions? This will just take a couple seconds. This is running on my laptop.
So I have a question.
Mm-hmm.
So did I catch you correctly that you can do a search that filters based on both the text criteria and, let's say, for example, here as well, the folder, you can say the folder matches something.
Yep.
And some other column matches something with select.
Like a date range or something.
And then also then the text index.
Mm-hmm.
All in one, so multiple criteria. Some are text search and some are SQL filters.
All in one. So you specify the filters as filter queries, which is a parameter in our search query. Yeah. And then here, we commit the index. So in this case, when you index the data, you have to commit the index. This because Solr is transactional. So when you're indexing, let's say something happens, the system goes down or anything occurs, this way you're not affecting the system and you're not affecting the index in any way while you're indexing new data. So it doesn't leave it in sort of a zombie state or a halfway state. It just rolls back to the previous version of the index. So now let's run through some searches. So we can search, and I'll show you what this is doing in just a second. So what we're doing here is we're just, when we do a GPText search, what it's returning is actually just the document ID as well as the document score, so the relevancy of that particular document to your search term. When we join that back with the original table, we're getting the full results back. So here we're searching for, on the content field, within 2 words, we're looking for the words Phillips and petroleum. So we're trying to do a proximity search between these 2 words. And we're looking only for emails to Christine Stokes. So this is where we're talking about the structured data. And date from January 1st, 2000 to January 1st, 2001. So here we're just returning the ID score and the to field. So you can see that these documents contain these search terms and have been filtered out by any email sent to Christine in the year 2000. Now, let's actually get that data. So what we're doing here is we're actually looking for the unified query parser. So as I mentioned, there are multiple ways that you can write your search queries. So we're looking for the content Phillips within 2 words of petroleum and this other term, so otherwise star. So any word, basically otherwise, is what we're looking for. And what we've done here, we've slightly modified the query. So we've actually placed the filters in a different parameter. So it's a little bit easier to read, it's a little bit easier to understand, and you separate the actual structured filtering from the search query itself. So now we see that only one of those documents actually contained it. So now we can actually go in and let's look at the content itself. So we can see Phillips and petroleum is right here. And the word otherwise appears up here. So you can see how this document matched that particular search term.
No shred. Nothing there that says shred.
Nothing there that says shred. So let's take a look at Solr Options. So there are multiple different Solr options that are provided. In this case, we're just going to be looking at one particular one. So let's say you have a document set or a table that contains multiple billions of records, and you're like, okay, I don't need to return all of these. I just need to return the top, 10, 20 results, and I can join that back. So what we can do here is we can limit the number of rows that are returned. So this is similar to your limit query. We're just basic in SQL. You can specify, I only want to return the top rows from each of the segments. Other ones that you can do are something called minimum match or specify the query parser. So you can specify a different query parser for your actual query versus the one that you use for your index. That may or may not be good depending on your use case. Generally, you want to use the same query parser for your search and your index. Minimum match is actually a really cool feature, which says, essentially, if you have X number of search terms, let's say I want to search for word 1, word 2, word 3, word 4, but I only want to return documents that match at least 3 of the 4 words, then you can specify minimum match with this particular term. And it will return basically only the highest ranking results. So here we can see we returned only the top 2 results from all of the documents. Because in this case, the rows argument is happening on a segment basis. So we're returning the top row from each segment. And there are 2 segments in this database instance that I have, or Greenplum instance. Another one that we can have is highlighting. So as I mentioned, we enabled the term vectors. So we're able to see exactly the positions of the documents, or positions of the terms in each of the documents. And when we search for them, we can place tags around these terms, custom tags that allow a user who's building an application on top of this to be able to highlight those particular terms. So as you can see here, we're highlighting Phillips and petroleum, so all instances, and we're placing these tags around it, around these as well. Some of the other things that you can do are faceted search queries. So if we take a look at the faceted queries here, we can specify faceted searches. So this is similar to kind of like building a pivot table. You can specify facets across each of the individual structured queries that you might have. So for this example, we're doing the same search term that we were doing before in this particular date range, and we're faceting by the from and to fields. So we're trying to see, who have these emails being sent from and to, so we can specify like different threads and different chains and how long these different threads might be. Oh. Leave. Well done. Oh, that's why. So we're faceting individually on these ones. So there have been 105 emails from Philip, 143 emails to Philip. Seems like he likes to email a lot but doesn't receive many responses. But yeah, you're able to facet on that. Another thing that you can do is facet on range. So if I want to see how many emails have been sent across a particular year or a particular series of years from, in this case, 2000 to 2005.
What's the definition of faceting?
Faceting is basically bucketing. So bucketing it into different groups. So we have a faceted field search, so you can basically bucket on a given field and see, for example, if we look at Enron, we can say who are all the emails coming from. So you want to facet on that and see who are the top senders and bucket it based off of that. Another thing might be, what are the dates? So how many emails have been sent across each year or each month? Another one that you might want to do is across a particular query. So you can say, I'm searching for this query where I bucketed into a non-standard group. How can I see, how many, emails might be in each of these different groups? So it allows for this advanced bucketing, which you can use for grouping your components. Another great use case for this might be if you have a bunch of logs stored in a table across your various components and that are running on your cluster. What are the logs? Where are the logs coming from? So let's say I search for an error and a particular error term, and it appears in a bunch of different logs. How do I group it by component? So what are the which ones are failing most often? Which ones are not failing as often? You're able to bucket it based off of that. So that's another different purpose for faceting. Now, another thing that we can show here is partition tables. So Greenplum has this notion of partition tables, especially for extremely large ones. GPText originally would have to partition each individual table, or basically partition each individual partition of a table. So if you had a table with 100 different partitions, you'd have 100 different indexes. And sometimes you wanted to search through either the whole table or a subset of those indexes. How would you be able to do that? You would have to write a query for each individual partition, which wouldn't be fun. So what we did was we added this capability to view a full table that's partitioned and see the individual partitions and treat it as a single index. So what I have here is a partition table part Enron. So it's basically partition the data by year across the varying years. So if we were to search through each of these, we could see that each of them would be like year 2000, 2001, 2002, etc. So how would you search through that? The same, you run through the same series of steps to create your index. Nothing changes. It's actually, you treat it as a usual table that's non-partitioned, but GPText recognizes if it does have partitions and treats it as such behind the scenes. Now when it comes time to actually query the table, we can say here, search across the parent table, in this case part Enron, for that same term. And we're returning the top results here. But let's say I want to search through only a specific partition. So for partition 3, in this case, that might be a specific year. It returns the results only from that year. Or another one, it returns only the results from that year. So you can specify the subset of partitions that you might want to search through much more easily, rather than having to search through the whole table or write a specific query for each one. So with that, that kind of shows a lot of the capabilities for the index and search. We also have some management utilities. So as I mentioned, being able to configure your instance when you're creating a new index or you want to modify an existing index, we have something called GPText config. So GPText config has a bunch of different options. Let's take a look at modifying a particular index. So each index that you create has a specific schema file associated with it. So basically, you're able to modify which analyzer chain am I going to use for the indexing and for querying. How do I treat the different fields in that analyzer chain? Do I want to store the original data into my index? Basically, you have a lot of these different options. Yep.
What is an analyzer chain?
So an analyzer chain is the series of steps that are taken by Solr when it's processing a document. So as I mentioned, when you're creating the index, you're going through a series of pre-processing steps. So here I can bring up, so let's take a look at this collection. So let's say, hello world. Let me take some of this. Actually, hello world. This is Greenplum. And then modify it, change it to Chinese. Oh, English to Chinese. Copy that. Here, let's translate it to another language as well. And add that here. Oh. Now we're looking at the international text analyzer chain. So let's run through this. So analyzer chain is kind of visualized here. So first we're going through the world lexer tokenizer. So how do we tokenize this particular document? So we've broken it apart. Hello world, each of the individual characters, Greenplum, and then the Russian characters, Greenplum. Then we have something called the Chinese, Japanese, Korean width filter. So different characters might operate at different widths, which is, I'm still unclear from a linguistics perspective what this means, but you're normalizing the Chinese characters to a common width, to a common expression. But as you can see, it's not affecting any of the Russian or English text. Then you're doing a lowercase filter, so you're normalizing the words here. You have something called a world lexer bigram filter. So with Chinese, Japanese, Korean characters, you generally have them in bigrams, so pairs of characters. So it's pairing up the individual characters, but as you can see, it's leaving everything else unaffected here. And then a stop word filter. So if I added, and my name is Bharath. So we add that here, so you can see the stop words and, is, etc. are removed. This is actually also configurable. So let's say you have a specific document and you're trying to remove all instances of a particular term that might be common in your document, but might not be a common regular word. You can specify that in your stop words file, and it'll filter those out of the index. Then we have the stemming filter. So being able to stem the particular words to common roots. In this case, it's using a Porter stem filter, so it's a specific algorithm, but it doesn't need to stem any of these words right here. But if we add like mobility or mobile, you can see now it's stemming those words right here. Now, this would be interesting. Let's say we ran it through a different analyzer chain, in this case, like our social media analyzer chain. We would not get the same results. It would treat this as a single word. It would parse these out, but as you can see, it's not as effective as using the international analyzer chain. However, if we were to switch it up and say like www.google.com hashtag Greenplum at Bharath28 smiley face, sad face, hello world, something like this, and we ran this, you can see, for example, it's parsing out the @ mentions, it's parsing out the hashtags, it's equating emoticons as happy or sad. So you can use this for sentiment analysis or equate particular words. So if you search for happy and someone just has like, I'm so excited, smiley face, smiley face, smiley face, it'll return that because it's equating the smiley face to a happy or a sad face to a sad. So you can use this as something called the emoticons classifier filter. You can specify particular emoticons to particular words. You can map them easily. Whereas if we were to run this through that international one, we're not going to get the same results. You can see the emoticons are taken out because it considers that as just punctuation. It treats Bharath28, it takes out the hashtags. You're not able to see that anymore. So you can see that different analyzer chains will have different results across different data sets. And you want to optimize the analyzer chain. Now Solr and GPText have about 37 different analyzer chains that you can use. And this is growing. And you can also build custom analyzer chains by uploading your own jar files. So you can say, hey, I have a specific text that contains only this type of log data or this type of formatted data, but I want to use a different analyzer chain, my own custom one. You can upload that and you can specify it in your managed schema file.
So does that mean you can customize your search to specific industries with terminology?
Exactly. Exactly. So depending on the type of data, the words that you might have, the terms that you might have, you can specify your index and customize your index to map to that set of data easily. So here we can take a look at a sample index. So as you can see here, let's at the bottom of the schema, you can see here are the fields that are stored in my table. So BCC, CC, content, the date, etc. And you're able to see what type of analyzer chain am I using. So for different data types, we also map the GPDB data types to Solr data types. And depending on the Solr data type that it's mapped to, it'll use a different analyzer chain for each one. So for example, when it comes to content, which is text data type, it's going to use the international analyzer chain. Whereas the ID is a type long, it's not going to index that or map that to anything. It just stores it as the number. So you can see how the different types are stored differently and indexed differently and stored in your index. And you can specify for each individual column. You can get really flexible and say, hey, I only, for the content field, it's international text, I want to use this analyzer chain. For another field, like the email field or something, I want to use the email tokenizer analyzer chain, something like that. You can also store these term offsets. So as I mentioned, when we enable terms, now we're storing the terms and the positions in that document. So you can enable that here. You can also store the original field. So rather than having to do a search and join back with the original table, you can search and return the results directly from the index. So this is really great if you have a large data set and you're returning millions of results, but you don't want to join back with the table because it's costly. This is much more cost effective, and you can rely only on the index and not have to rely on the table. This is great if you have kind of a table that you don't update very often. You're indexing it once, and it remains static, but it's an extremely large table. So actually, we can one last thing, we can see the different types of analyzer chains. So what are the different ones that are here? Text, English text, it mentions it, and then here you can see what are the different types of filters that I'm using. So these are the actual components, each of the steps that you're using in that analyzer chain. Yeah. So with that, yeah.
So if I want to use supervised machine learning
Mm-hmm.
to classify documents based on some known documents that are, let's say, fraud,
Yeah.
and I want to train a supervised model to process the text,
Yep.
how would I get the information out of the documents to put it into the
Into MADlib?
learning model
Yeah.
so that it can run the training?
So here,
What is the question? Can you repeat it?
so essentially what we're looking at is how do we expose this terms so we can do the advanced machine learning. So what is the process to do that for the actual statistical analysis? Where do we start from GPText and pass it over to MADlib? Oh. As Hebrew, Russian, Arabic, and many other languages. I think it's really only limited by Solr, which can operate on at least a couple dozen of the major languages in the world. I'm not sure which ones are not supported, but depending on how you specify, if you want to upload a custom jar to be able to deal with a new language, you're able to do that. So you might have to write your own parser and your own analyzer chain and series of steps to be able to parse that particular language. But once you do that, then you would be able to search through it. So it is customizable and extensible to new languages. Yeah, no problem.
So, a couple of questions. You mentioned stemming earlier.
Mm-hmm.
Do you do the opposite as well, lemmatization?
There is some capability for lemmatization, but you would configure it through Solr. Yeah.
And does it support entity recognition?
So that's actually one thing we're in the process of building. So we're looking at named entity recognition. So what this means is being able to treat individual words and tag them as either an organization or a person or some type of category. So entity recognition, some of the popular ones that you might see are the Stanford NLP libraries, which have their own model for named entity recognition or even part of speech tagging. So we're looking at incorporating those capabilities into the indexing pipeline. So that way, if you say, hi, my name is Bharath from Pivotal in San Francisco, you can treat that as, tag it as name, organization, location, and then you can extend the querying to say, I want to search for all people at Pivotal. Then you can say I want to search for these people, so it'll return, Bharath, Ivan, Yogesh, etc., Oz, and it will return all the names that are associated with that organization.
One of the more difficult questions I've gotten from financial services customers
Mm-hmm.
is around not translation, but around transliteration. Right? So if you have the pictogram for the word in Chinese, way,
Yeah.
right, the translation is great, but the transliteration is way, W-E-I.
Mm-hmm.
And so to be able to search on someone's last name, which happens to be way,
Yeah.
right, and not look for great, but you're looking for W-E-I.
Yeah.
Do you have that kind of capability, or you rely on an external service to do that?
For transliteration, it might be a bit more difficult. One way you could potentially get around that is either protecting the name way. So if it was a capitalized, of course, it might depend on your data set. So you can say the name way, I want to protect that, but all terms that are lowercase way, in this case, a transliterated version, you can equate that to, you can use a synonym configuration to equate that to another word. And that way you can say, I'm searching for, let's say what does way itself stand for? Way?
Great.
Oh, great. Okay, so let's say you can map the word transliteration way to great. You can say, I'm searching for all instances of great, and it'll return the transliterated versions, but not the last names. So that's one way you might be able to get around it, but there's no direct method of transliteration. Yeah. No problem. Awesome. Thank you guys very much for attending this. If you have further questions, you can reach me at bsitaraman@pivotal.io or by my Twitter handle.
How about the documentation or any place they can go to read more?
Documentation, and the download is available right here. So gptext.docs.pivotal.io. Feel free to read through to try and understand and ask questions. If you want to mess around with GPText and actually play around with it, as well as Greenplum database, you're able to download it from PivNet or build it from our GitHub repo. Thanks.